These are the notes on velocity. So physics is the study of motion, energy, and forces acting on matter. And right now we're talking mostly about describing motion. One of the ways we describe motion is how quickly it is occurring. There's different ways of describing that, and we're going to discuss primarily one of them. Remember that a vector has both magnitude and direction, whereas a scalar has only magnitude. So a vector tells you which direction it's going, and a scalar does not. That's the important distinction. It turns out we have to treat these numbers differently. Okay, when we're dealing with vectors, we sort of have to stick with vectors. When we're dealing with scalars, we usually have to stick with scalars. We don't usually cross them with each other. I might as well tell you the old joke. Why did the mountain climber not get bitten by the mosquitoes? Why did the mountain climber not get bitten by all the mosquitoes that were around? Because you can't cross a scalar with a vector. Okay, so that joke, you have to realize that mosquitoes are vectors for illness, for the spread of disease. So they're also referred to as vectors. Anyway, bad joke, bad joke. Sorry about that. So displacement is considered to be a vector because it tells you which direction that you have moved. Distance is a scalar, so you could go 10 meters, but which way? 10 meters east is displacement. So displacement has to be much more specific, okay? Or 10 meters upward, that's also a vector. Velocity, what we're here to talk about today. Velocity is what brings us together today, is a vector. Velocity, vector, VV. Speed, on the other hand, is a scalar. Oh, SS. So that's kind of cool that velocity is a vector and speed is a scalar. Maybe repeat that to yourself a few times and you won't forget. So for example, you could be going 80 kilometers per hour and that is your speed. But if you're going 80 kilometers per hour north by northeast, well then that suddenly becomes a velocity and it's a vector, okay? So velocity has to tell you which direction you're going. If it doesn't tell you that, remember, it is not a velocity. However, speed is still a technical term in physics. So that doesn't mean that we never use the word speed. It is a valid term. It's not like speed is the weaker term and velocity is the more educated term. It's just they have different meanings in physics. So that brings us to average velocity. Why am I saying average velocity and not just velocity? Because you can have an instantaneous velocity that might vary from millisecond to millisecond or even second to second. But what we usually concern ourselves with is the average velocity over a certain period of time. Now the way that we represent average is by drawing a line above the variable. So velocity is a lowercase v and it has a little line on top of it. That means we're talking about the average velocity. And then delta d means the change in distance, the displacement, and delta t means the change in time. So how much distance did you cover in how much time? That is your velocity. Now, the textbook doesn't use a lot of d. What it uses is, because it assumes you're going along the x-axis, it replaces d with x. So for the purposes of making things easier, to get in alignment with our new textbook, I am going to do that too. When we do that, the only thing that changes is from a delta d, now we have a delta x. This is the same thing. It just depends on what you call it. So if you're moving along horizontally, along your x-axis, okay, then that is your delta x. Okay, so that is still displacement. And then delta t is the time. How much change in time have you had? And when you divide those, you get your velocity. And you have to know which direction this is in, of course, because velocity is a vector. So how do we figure out delta x? Remember, delta x is the same exact thing as delta d. This is just the terminology the textbook uses. So how do you find delta x? Well, you take where something ends, its final position, xf, minus where it started, its initial position, xi. Okay, you have to know which direction it's moving, of course, because this is a vector. And so it's x final minus x initial. So let's say you started at 2 meters and then you moved to a position that was 12 meters to the right. Well, 12 minus 2 is 10 meters to the right. So then that would be your delta x. Delta t is also similar. It's your final time when you ended minus your initial time. So let's say you ended at 24 seconds, but you started at 13 seconds. Well, it'll be 24 minus 13, 24 seconds minus 13 seconds, and you would have 11 seconds. And then if you moved 10 meters to the right in 11 seconds, well, you would divide 10 meters by 11 seconds, and you would get a little bit less than 0.9 something meters per second to the right. So average velocity can be written this way, we just said. And then if we want to get real fancy, we can replace the delta x with the way that we find it. But this makes the equation more cumbersome, but I'm just going to show you in case you need to use it. So this is also the definition for average velocity. Average velocity equals x final minus x initial divided by t final minus t initial. And that's the same thing, it's just how you get those numbers. It's how you obtain those numbers. So either way you want to do it, I prefer to find delta x first and then just put it in the equation, and delta t first and then just put it in. But if you want to do it this way, it works. Just make sure to follow the order of operations. Subtract before you divide. So this brings us to the equation for the position of an object. Notice that this equation is based on average velocity. If we want to know the position of a moving object at any given moment, that's what x is, the position, it equals the average velocity times the amount of time since your reference time where you began, where you considered it 0, plus the initial position. It's important to add in the initial position, okay, because if it didn't start at 0, it might have a head start. Or if it started behind 0, it might have a negative value, okay? But it's usually easiest to start things at 0. And I'll try to show you that when you do start things at your definition of 0, because you get to choose it, your reference frame, then it makes the calculation much simpler. So very frequently, especially when we're only dealing with one moving object, well, you might as well start it off at position equals 0. Why make things more complicated than you have to? So you'll see what I mean when I show you the next few graphs. Here is a graph showing the position versus time. So notice that all those points are plotted and then you connect them with a line. Now that doesn't mean you have to use the plotted points to do your calculations. You could take any point that's on that line. Now since for now we're using things traveling at a constant velocity, that means that those points do line up into a nice and straight line. The slope of that line will tell us the velocity, okay? And you'll see that in our next graph. So here we see a position versus time graph and one of the definitions for average velocity, including the final and initial positions. So for your final position, you can actually pick anywhere, but I'm just going to pick the very last position that is shown on this graph, right there. So what's our XF? Our XF is 12.0 meters. And what's our TF, our final time? 7.0 seconds. So Now, to make things easier, we did start this graph at 0, position 0 and times 0. Why not do that? Because you get to choose your frame of reference, and that makes xi 0 and ti 0. Well, subtracting 0 makes absolutely no difference. So actually, my xf is going to be equal to my delta x. My tf is going to be equal to my delta x. This is why we often like to start at time equals 0, position equals 0, okay, and move in a positive direction. If we choose the direction we're moving as positive, that also makes our life easier. So if I define my average velocity that way, then all I have to do is divide these numbers to get my average velocity. That means over the course of that period of time, it was moving 1.71 meters every second. 1.71 meters per second. Meters per second is a unit of velocity, okay? And which direction is this going? Well, it's going in our positive direction. So we could say, you know, whatever we chose as our positive direction. To the right or forward, okay, that is our positive direction. Now, the equation for position depends on xi also. But since we've started at 0, that's our initial position was 0, that will drop away from the equation. So our position will equal, okay, average velocity times time. That's why it's another reason to pick 0 as your initial position. Since you get to choose it, that's often what we do. Now, what would it look like if our initial position was not 0? Let me show you that. This blue line is not starting at 0. Our initial position is 3.0 meters. Notice that it's going at the same velocity. You can tell because those lines are parallel. It's the slope of that line that tells you the velocity. But it's been sort of shifted upward, correct? So everywhere you are on that blue line will be 3 meters ahead of anywhere you are on that green line at the same moment. So you can tell, even though it goes off of the graph, you can tell what that position would be at time equals 7 seconds, even though it goes off the graph, because the green line was at 12, so it would be 3 meters ahead of that. It would be at 15.0. So notice that velocity shows up as the slope of the line, and then you can think of the xi as sort of like your y-intercept, where it hits the y-axis. You can think of this as one of those y equals mx plus b. I know that's funny because we're using different variables in different positions there, but that's your standard algebraic equation, okay, for a sloped line with a y-intercept. Y equals mx plus b. So in this case, average velocity would be your m, and then xi would actually be your b, your y-intercept. Here is another graph showing two different joggers and their position versus their time. So you can see that each jogger is keeping the same velocity. Each jogger started at the same initial position, but they are going at different velocities, so they get more and more increasingly spaced out. Okay, so again, we're starting at 0, so we don't really need to put in xi and ti. When we subtract 0, it doesn't change it, so I can replace it with this equation. So in this case, notice if I pick a position for the red jogger, well, I'll just pick the one that's right there. Notice you could say that my xf is 2.0 meters. But then, of course, my xi is 0. So my delta x is also 2.0 meters. My tf is 1.0 seconds, but my ti was 0. So my delta t is 1.0 seconds. So what's my average velocity for the red jogger? I divide those. 2 divided by 1, 2.0 meters per second. So that is what is represented by the red jogger's sloped line. That is going at the velocity of 2.0 meters per second forward. We're assuming that it says position, they're positive numbers. So that's forward. They're both going in the same direction. We've chosen that to be our positive direction. What about the blue jogger? Well, the blue jogger has also moved meters, but it took longer to get there. Okay, it took a lot longer to get there. By the way, going 2 meters in 2 seconds is not very fast, let's just say. Okay, so then I'm not talking smack about the blue jogger, but okay, so then if you go down, then by the same token as before, the blue jogger, his TF is 2.0 seconds, but his TI was 0, so 2.0 minus 0 is 2.0. And then for the blue jogger, when we divide 2 by 2, 2.0 by 2.0, we get 1.0 meters per second. So notice that the blue jogger is going at half the velocity of the red jogger. So that's what it looks like. Okay, the slope of the line tells you the velocity that they're moving. And of course, these two joggers started out together at the same moment, in the same position. They're both moving in the same direction, but as time goes on, the spacing between them grows. And you could use this to calculate the space between them at any given moment. Okay, that would be the space between the two different sloped lines, the vertical space. And of course, for both of these, you can predict their position with time using this equation for position. And for both of them, xi would equal 0. So that would drop out of the equation, just sort of cover that up. So just read the x equals average velocity times time. That would be enough to predict their position because we started at 0. So look at all the benefits for starting at 0. So please try to do that when possible. Here we see an example of two different moving objects, A and B, both moving in the same direction, in a positive direction, let's say forward, and they're going at different velocities. Which one is going faster? There's a few things going on here. There's A and B, and they don't both start at the same place. So one of them kind of got a head start. Can you see which one had a head start when this began from the perspective of the direction they're moving? Okay, object A started at 0. That's actually a head start. Why? Because object B was at negative 50 meters. That's far, far behind compared to the direction they're moving. So B had to play catch up, and notice that it took 45 seconds for B to actually catch up with A. So A started ahead, was going slower, but still was ahead for 45 seconds, and that's where the two lines cross. So in this case, xi for object A would be 0. But xi for object B would be negative 50. So you would have to do, for object B, you'd have to, for the position equation, you would have to do x equals average velocity times time, yes, minus 50 meters. So every calculation is going to be set back. So it had to overcome that sort of head start that A had. It had to catch up with A. Now I want to show you a graph where something different is happening. Can you tell what's happening here in this graph? What is different about this graph? Well, you could say the line isn't going up, it looks like it's kind of going down. So does that mean it's not moving? No, it is moving, but what's the difference here? Well, let's look. At time equals 0, if you follow that up, our position is 20 meters, positive 20. At time equals 4, our position is 0. So we've gone from 20 meters to 0. Oh, so what does that mean? That means we are going backward. Depending on which way we have defined positive numbers, we are going the other way. So if we define going to the right as positive, we are going to the left. If we define going forward the way you're facing as positive, then we are going backward. We're backing up. Okay, so think of a car in reverse. So what would our delta x be in this case? Okay, in this case, it would be 0, which is our final xf, minus 20 meters. So 0 meters minus 20 meters, because our xi is actually 20 meters. So 0 minus 20, what does that give you? 0 meters minus 20 meters, that gives me negative 20 meters. So because of the way we define position, of course it's possible to have negative positions, like we saw in the previous one, how object B was set back from object A. So you can have negative changes of position, negative displacements. Okay. And what about our time? Well, our final time here would be 4, and our initial time was 0. So 4 minus 0, well, time is going to be positive. Time pretty much has to be positive, okay, as far as we know. And that gives us 4 seconds. So negative 20 meters divided by 4 seconds, what does that give me? We don't get rid of the negative. It gives me negative 5 meters per second. That is what we call a negative velocity, okay? Or depending on your frame of reference, it means you're going backward. And of course, when you are calculating using this velocity, you have to put a negative number in there for average velocity. And that doesn't mean that your other numbers all have to be negative, because xi, what would xi be in this particular case, for this particular circumstance? Xi would be 20 meters, positive 20 meters. Because look, that's the y-intercept. That's where it started. Our initial position was positive 20 meters. Okay? And then using that equation, you could calculate the position at any given point in time, even when it's in between the whole seconds. Even if it's in between 1 and 2 seconds, you could get a more precise number. Now let's calculate a velocity for an object that does not begin at what we have defined as 0. Remember, it's better to define an object as starting at your reference point of 0, since you get to choose it. But let's say you couldn't do that for whatever reason, and instead we wind up with this. Now notice it doesn't exactly start on 2, it doesn't exactly start on 3, and it might be hard to nail down that exact point. So remember, if you're getting the slope of a line, you should know this from algebra, that you don't need to start at the beginning and go all the way to the end. It's usually a good idea to get a good length of the line as much as you can, but often there's a neat trick. You want to pick a position where it intercepts the grid, where the line crosses over an intersection, like right there, and that would be our final position, okay? So at that final position, since it's right crossing on the grid, it lines up with 6 meters, and it lines up with 9 seconds. So my XF is going to be 6.0 meters. My TF is going to be 9 seconds. Okay? And we need another position that's on the line, but let's look for another place where it crosses the grid. It crosses right there. So you could say, well, I could have picked a longer segment of the line to get a more accurate measurement, but actually that's a good enough length. And it matches up to 4.0 meters and 4 seconds at that particular position. So let's see. So what is my delta x? Now we don't start at, we did not start at 0, so there is an xi, okay? And even if we did start at 0, we're picking a point that's further along the curve. So basically my xf is 6 meters, and my xi is 4 meters, so 6 minus 4 gives me 2.0 meters. So 2.0 meters, and that's positive because notice the slope is going up and to the right. That's a positive slope, so we are moving forward. Okay, and what about my delta t? Well, my tf is 9 seconds. My ti is 4 seconds. So 9 minus 4 gives me 5 seconds. So what's my average velocity? Average velocity, divide them. Okay, well, I have to divide 2.0 meters by 5 seconds. So obviously, it's going to be a number less than 1 because the numerator is less than the denominator. And when I divide those, I find that my average velocity is 0.4 meters per second. So notice, you can find the velocity as long as you have 2 points. I would recommend not picking points that are right next to each other, because that is a good way to get inaccuracy, to introduce less accurate measurements. You want a pretty good distance, but this is more than half the distance. This is pretty good, and I can calculate a pretty good average velocity. Okay, so that's how you calculate the average velocity. using 2 positions on the line, and also just showing you when a line does not intercept at 0. So I wanted to show you the difference between a few different position versus time graphs. Here's one. We'll call this object A. Object A is moving in a positive direction, and these are the plotted positions over time. It's obviously traveling at a constant velocity, or very nearly constant, so that you can't tell the difference. Okay. Then we have object B doing that, and object C doing that. So notice that they're all traveling at a different velocity. You can tell by the different slopes, but we started them all at the same position. We started them all at 0, because of course we would if we could. If you can start them all at the same position, it makes all your calculations easier. So that's why I always recommend starting at 0 whenever you can. So how would this relate to their velocities over that time? Well, as I said, it's a constant velocity. So we can also make a velocity versus time graph for these. And now let's look at a velocity versus time graph for those same objects. Notice that the y-axis has changed now. It is no longer meters, it's meters per second. Okay? And the x-axis is the same, it's still time in seconds. By the way, let me point out right now that having that meters per second makes the difference between having a correct answer and an incorrect answer. It's just like putting a unit after every number. It's that important. Labeling what your axis is and with a unit is like putting a unit after every single point on your graph. So what would it look like? Velocity versus time for object A that we saw in the previous graph. Well, it had a constant slope, and this would make more sense to those of you who are better at calculus, but that means the derivative would always give you the same value, and so velocity would look like this for object A. Why? Because it was going the same velocity the entire time. From time equals 0 to time equals 10, it was going at the same velocity, the same average velocity. So it would be 0.8 meters per second. That is what it turns out to be. If you go back and divide, you can see that. Okay. So what about object B? Object B, remember, had a lower slope, and that means it has a lower velocity, but it also had a constant velocity, so it would also be a straight line on the velocity curve, okay, on the velocity versus time graph. And then C, of course, had an even lower one, and just like you'd imagine, it would rank even lower. Now, this is kind of a boring graph, but it helps you understand that the velocity is steady for the entire duration. So we're going to see later what happens when it's not, but for now, it's important that you understand how the position versus time graph relates to the velocity versus time graph. Here they are side by side, and so you can see what happens. Okay, again, it makes more sense. The more you know about calculus, the more sense it makes. You can do this without calculus, of course, and you could say that one is the derivative of the other is the integral of the other. You could go back and forth between them using calculus, okay? And that actually continues to happen when we get to the next step. I just wanted to make this really, really clear what these graphs mean. So you'll be doing graphs like this in the new assignment. You'll be doing a graph of the position versus time and the velocity for the objects that you did on the previous assignment on the motion diagrams. So it's not super challenging. It's just getting you to think about what it would look like, making an appropriate scale. Don't forget to label every axis, okay? And I do want to see the velocity versus time graph as well. And you can make them smaller. Usually my recommendation is to make your graph fill up a piece of paper, but these you could put side by side and you could fit them maybe a total of 4 graphs on each side of a piece of paper. Maybe fold it into fold it twice so you can see how much space you should use. Okay, I've got to be able to see it, so it shouldn't be very tiny. I do want you to carefully position the points so that it is accurate and base it on your motion diagrams. The rest of the instructions are on the assignment, the rest of those instructions. So that is the end of the notes on velocity, and we will continue with our unit on motion in our next notes.